Welcome, fellow engineers and IT enthusiasts. Have you ever stared at a red CI/CD pipeline, wondering why it failed again? Or perhaps worse, spent countless hours debugging a mysterious deployment issue that could have been foreseen? Today, we're diving deep into how predictive analytics, supercharged by generative AI, can transform your Java DevOps pipelines from reactive firefighting to proactive forecasting. Imagine knowing about potential build failures or deployment bottlenecks before they even happen. That's the power we're unlocking today, using historical CI/CD data and a touch of AI magic. We'll explore an example-driven tutorial, complete with data and model integration concepts. Let's face it, CI/CD failures are more than just an inconvenience. Each red build, each failed deployment, carries a significant cost. There's the immediate cost of lost developer time spent debugging, manually rerunning pipelines, or patching production issues. But beyond that, there's the ripple effect: delayed feature releases, missed deadlines, decreased team morale due to constant firefighting, and ultimately, a negative impact on your product's reliability and your business's reputation. Traditional monitoring tells you what went wrong, but predictive analytics aims to tell you what might go wrong, allowing you to intervene proactively. This shift from break-fix to predict-prevent is a game-changer. So, what exactly is predictive analytics in the context of DevOps? Simply put, it's the application of statistical and machine learning techniques to historical CI/CD data to forecast future outcomes. Instead of merely logging past events, we analyze patterns in successful and failed builds, deployment durations, test results, and error messages to identify precursors to future problems. Think of it as a sophisticated crystal ball for your software delivery pipeline. We look for anomalies like sudden increases in build duration, recurring test failures, or specific error message patterns that often lead to bottlenecks or complete system outages. The goal is to move from reactive problem solving to proactive optimization. Now, you might be thinking, traditional machine learning can do some of this. And you'd be right. But here's where generative AI truly shines and gives us a massive advantage. While traditional ML models are excellent at numerical predictions and classification based on structured data, they often struggle with the vast amounts of unstructured text data found in CI/CD logs, things like error messages, stack traces, and build output. GenAI, particularly large language models, LLMs, can understand the context and nuance of these logs. They can classify complex error messages into meaningful categories, identify potential root causes by correlating different log snippets, and even suggest actionable remediation steps, all in natural language. This ability to reason over text data elevates our predictive capabilities significantly. At the heart of any predictive analytics system is data, and in DevOps, that means your historical CI/CD metrics. What kind of data are we talking about? We need detailed records of every pipeline run, a unique build ID, the timestamp of execution, duration seconds to complete, the overall status, success or failure, test count and failed tests, whether deployment success occurred, and crucially, any error message or log excerpts. The more comprehensive and consistent your data, the more accurate your predictions will be. This data typically resides in your CI/CD platforms like Jenkins, GitLab CI, GitHub Actions, or Azure DevOps. Our example project uses a simple CSV file to simulate this historical data collection, demonstrating the format and type of information essential for forecasting. To demonstrate these concepts, we've put together a Java-based example project called CI/CD AI Forecaster. This isn't a production-ready system with a fully trained GenAI model, but it provides a robust architectural blueprint and simulates the crucial GenAI interaction points. The project's core idea is to analyze past pipeline runs to identify patterns that precede failures or bottlenecks. It showcases how you'd structure your application, load data, apply predictive logic, and where a generative AI component would conceptually fit in. This foundation allows us to explore the possibilities without needing a full-blown LLM API key for every demo. Let's peek under the hood, starting with data ingestion. Our build data class acts as a simple plain old Java object, POJO, modeling each historical CI/CD record with fields like build ID, timestamp, duration seconds, status, failed tests, and error message. This POJO is the structured representation of our raw data. The historical data loader service then takes on the crucial task of reading this data. In our example, it parses a historical_builds.csv file. In a real-world scenario, this service would be responsible for integrating with your actual CI/CD platform's APIs, fetching build logs from Jenkins, pulling pipeline metrics from GitLab, or querying Azure DevOps for deployment statuses. The cleaner and more consistent your data loading, the more reliable your predictive models will be. The prediction service is where the magic happens. It takes the loaded historical build data and begins its analytical work. Even before involving GenAI, traditional rule-based and statistical analysis can yield valuable insights. Our service identifies 1. Recent failures. It checks for any builds that failed within a configurable window, say, the last 3 days. A cluster of recent failures, even if seemingly minor, can indicate an underlying instability. 2. Long-running builds. By setting a threshold, e.g., builds over 400 seconds, we can flag potential bottlenecks. A build consistently taking too long might be suffering from resource contention, slow tests, or inefficient build steps. These early warnings are crucial for maintaining pipeline efficiency. Now, let's talk about the exciting part, the generative AI simulation within our prediction service. While we're not making live API calls to an LLM, our classify error message GenAI method demonstrates how a GenAI model would process unstructured error messages. It takes a raw error string and returns a classified category like test failure, database connection issue, or resource exhaustion. In a real system, this method would construct a prompt with the error message in context, send it to an LLM API, like Google Gemini, OpenAI GPT, or AWS Bedrock, and then parse the LLM's intelligent response to extract the classified type and, potentially, suggested remediation steps. This is where GenAI moves beyond simple keyword matching to contextual understanding and problem solving. Ready to see it in action? Setting up the CI/CD AI Forecaster project is straightforward. First, ensure you have Java Development Kit, JDK, 17+, Apache Maven 3.6.3+, and Docker Desktop installed. Begin by cloning the repository. Then, navigate to the project root and run mv and clean install to build the application. Once built, you can execute it directly from the generated jar file using Java jar target/cicdaiforecaster.jar. For a containerized experience, which is common in DevOps, you can build the Docker image with docker build t-cicdai forecaster, and then run it using docker run cicdai forecaster. Or even simpler, docker compose up build will handle everything. These steps provide a quick way to get the predictive analysis running locally. Once you run the application, you'll see a predictive analytics report printed to your console. This report is your forecast. It will highlight recent build failures, categorized by the simulated GenAI, test failure, database connection issue, etc., along with high-level GenAI suggestions for common root causes. It will also list potential bottlenecks by identifying unusually long-running builds and providing GenAI insights on optimization.